All right, welcome to our first tier list for Calculus 2. All right, today we're going to rank the functions that we see in Taylor series, power series, by terms of their growth rate. Okay, so the top of the tiers will dominate the lower tiers. All right, meaning to go to infinity faster. All right, we're looking at the limit as n approaches infinity. Now, every function has parameters that can have outsized influence at low values of n. And that's what makes this really challenging to see, all right? Because we're not talking about when n equals 1 or 100, 100 million, or even 100 to the 100 million, all right? We're talking as n goes off to infinity, all right? And so some of these might be surprising because we're thinking of very even large values of n, all right? The relationship is not going to be known until we go all the way off to infinity. So if anything you're unsure, feel free to pull it up in Mathematica, GeoGebra, give it a whirl and see what we got, okay? So now, where are we going to start? Okay, I think the best place to start is at everyone's favorite function, right? We're going to start with n to the p. All right. Now, n to the p is an extremely flexible function. It's everyone's first function, right? Linear functions, quadratics, all of this. When I say flexible and deceiving, it's because, well, right? If I have p less than 1, then I've got some concave type functions. If p is bigger than 1, it looks convex, kind of like e to the x. So where does it go? Is it down here in the low tiers? Is it up here in the high tiers? All right, well, that flexibility, all right, I think it's going to put it solidly right in the B tiers where we're going to put these polynomial growths. Okay, now here for polynomial, we usually think of just integer values, right, or natural numbers. Okay, but here I mean p could be any real number. All right, when I say polynomial growth, I just mean that the power is fixed and the base is what's going to increase. And I just want to say that I think B tier is a great place for this. Okay, it's a great support function. All right, what do I mean support function when it comes to series? Well, it impacts the endpoints of the interval of convergence, right? But it's not going to impact the radius. Okay, if you see this in your Taylor series, all right, it's not going to change. It's not going to have any role in the radius of convergence, right? But you can mess with the endpoints of convergence, right? This is also true of log that we'll look at, but this end of the p has much more interesting cases. All right, these power functions, okay, maybe the left side only converges, maybe the right side converges, maybe both is included. All right, that kind of flexibility is something that log can't have. All right, and since we're talking about log, let's just get it out of the way, okay? Because this function, we're going to talk about it a lot, because log to the q here is an absolute potato. Okay, it grows so slowly, all right, that the rate of change, if you calculate the derivative, right, completely ignores multiplicative scaling. What do I mean? Right? So we all know that the derivative of log x is 1 over x. All right? Well, what's the derivative of log 7 times x? Multiply by 7 inside the argument. I should be, right, increasing faster. I've scaled it. Nope. Still 1 over x. Log don't care. All right? So its job is just to kill growth. It goes up to infinity, yes, but horrifically slowly. Okay? Take any power of log. All right, I think what's really surprising. Take any power of log. Let's look at the limit as n approaches infinity of log of n. I don't know, let's just keep adding zeros. All right, and let's divide that by n to the 1 over. Let's just keep adding zeros. All right, so log to a massively high power, n to a tiny fractional positive power. That's 0. Log is completely trashed. Any power of log is completely trashed by even the millionth root of n. And finally, tell me anything that you remember about the log function. The log laws? I doubt it. All right. Its derivative? Most likely, probably. All right. Do you remember the fact that I mean the natural log when I just say log? All right, that alone makes it completely potato tier. All right, this function is utterly unforgettable. We're going to look at some interesting things when we contrast with the other functions on this list. Um, but like I said, absolute potato. Slowest of the slow. All right. So, where do we go next? All right. Um, we mentioned it already, so we might as well talk about it, right? Which is these exponential functions, right? B to the n. I think these are interesting because it's the biggest difference in rating between like a novice, right? Like what you thought when you first saw exponential functions. Maybe in pre-calc, right? You're in pre-calc, you're like, oh, these S plus tier for sure, right? You learn L'Hopital's rule, right? You learn L'Hopital's rule in Calc 1, and you're like, exponentials, certainly S tier, it's amazing. Then we get to Calc 2, we see more exotic functions, and we realize exponentials probably just like A tier, right? It grows faster than polynomials, but we can do a lot better than that, right? So it certainly dominates polynomials, but it's not the strongest. Okay. So what are the strongest, right? What are these functions, okay, that we want to see, that we didn't see in Calc 1, all right, that we're starting to see now, that are in this S and S plus tier. Okay. Well, there's only two left, right? Which is n to the n and n factorial. And these ones are going to be hard to place because, like, one of the first things that you learn to think about these functions is you say, oh, all right, n factorial is kind of like n to the n. Okay. Well, n factorial, that's going to be our S tier function. All right. So what that means, right, is the limit as n approaches infinity of n factorial over n to the n, right, is going to equal 0. Okay, it's dominated by n to the n. All right. How dominated? This is an interesting thing. We talk about these tiers, right? So if we look, so A tier and above, right, we're going to impact our radius of convergence. Down here, we're doing the endpoints only. Okay. And then even more, all right, so this rarefied air, why is this S tier, right? Because if we see these, right, our radius, if it's in the numerator, all right, our radius is 0. It's in the denominator, our radius is infinity. Okay, so these S tier functions, right, that's why they're S tier. All right, they're going up to infinity so fast that they make our radius infinite. Okay, now here's some interesting things. Okay, how much of a gap is there? Okay, so if we do the ratio test, we can kind of find, so one of the things, so n to the n, that's our S plus tier. All right, that's S plus. Okay, so if we do the ratio test, okay, so if we look at the limit as n approaches infinity, so here a sub n is going to equal n factorial over n to the n. I'll flip it. All right, and we look at the ratio of n plus 1 to the n plus 1 over n plus 1 factorial times n factorial over n to the n, right? Look at this limit. What is this going to give us? Well, this is the limit as n approaches infinity. Okay, so we'll just combine some like terms. The n factorial is going to cancel, leaving me with 1 over n plus 1. And then I'm going to be multiplied by n plus 1 times n plus 1 to the n over n to the n. Those are going to cancel again. So this is the limit as n approaches infinity of 1 plus 1 over n to the n, which is e. Okay, so I give it a suggestion, right? So it's natural to think, okay? It's natural to think that, well, all right, so sure, the limit of n factorial over n to the n, right, we know equals 0. N to the n dominates it. Okay. Well, what if I slap an e to the n up here? What if I slap an e to the n up here? Because if I use the ratio test between of n to the n over n factorial, right, which is how we sort of see the growth of exponential functions, the growth of the geometric series, right? We're saying, oh, like my rate is like e. So that ratio between those two terms is kind of like e when it gets large. So does that balance it out? No, it's too much. Okay, it's actually too big. That's going to go up to infinity. Okay. But this also tells us, though, is that the difference has to be on like polynomial logarithmic, right? It's got to be sub-exponential. It's got to be sub-exponential, right? Because it can't be picked up by the ratio test, but it still has to be impacting our growth off to infinity. And so it turns out the right kind of, to balance these terms out, so n factorial e to the n over n to the n times root n, this is going to give us a finite number, and that's square root of 2 pi. Okay, so that's about how much bigger n to the n is. All right, this is my factor that I need to account for n factorial versus n to the n. Okay, well now the question is, okay, well, like what's C tier, what's D tier? Okay, well, this is where our friend log comes back in. Okay, because there's some interesting things that we can do. Because what we can do now is we can start, all right, we can compose these things. Well, let's look. What's like log of b to the n? B to the n is a tier above our polynomial. Log is below tier. Maybe if I compose them, right, I'll get something. Well, no, actually, you don't. You just get n log b, which is linear, right? So, like, I don't know, it's pretty sad. But like, I guess, I don't know, linear beats, so only better, right? Only better than case for polynomials with p is less than 1, so, I mean, I don't know, right? Like, sure. Like log of b to the n. Let's put that here, right? Because it's just, I don't know, it's kind of dumb, it's just linear, okay? So that's not good enough. Well, what about log of n factorial? Okay, n factorial grows amazingly. Well, let's look, right? Let's remember our log loss. Well, this is going to be equal to the sum, right? The sum from I equals 1 to n of log I. Because this is the product, right? This is log of n times n minus 1, so on and so forth, right? Products become sums, okay? Sum, remember, right? So we have the integral test, right? The integral test, we have series is kind of like the discrete integral. So this is kind of like the integral from 1 to n of log x dx, which is, you know, n log n minus n. All right. So now this is interesting. Okay, because this beats linear. All right, this beats linear, which again, this just grows. All right, so n log n minus n. You know, we only care about the dominating term. That's n log n. Okay, so there we go. Let's do log of n factorial y, because the limit as n approaches infinity of n over log n factorial, right, equals 0. So log n factorial beats linear functions. It's pretty good, right? Beats linear functions. Okay, it doesn't. It's not. We don't quite get those values of p above 1, but we at least beat the linear. But here's what's crazy, right? Going back to how much of a potato the log is. What is n log n? N log n is log of n to the n. So if we're looking, log of n factorial, right, is like log of n to the n. What do I mean by that? Well, the limit as n approaches infinity, log of n factorial over log of n to the n equals 1. So the logarithmic function is so terrible, right? It grows to infinity so slowly that it eliminates even the gap between s plus and s. So log goes so slowly, right, that it cannot even tell the difference between these functions of higher tier. Okay. Now, I think one thing that you could possibly do or consider, right, is n to the n the fastest growing function? Obviously not. All right. What I tried to do is just really show the gap between our polynomial growth and our logarithmic growth. Like log is terrible. All right. It is really slow, so I want to show that gap. I think, what's defensible. All right. What else is defensible? We can move everything down tier. I could say n to the p is c tier, b to the n is b tier, n factorial and n leave together. Maybe, I think also this is reasonable. Put these in the same tier, except for I want to change the order, right? So right, and then like what's in the S plus tier? Well, like I think something that's interesting is look at, okay, obviously what we want to be looking at as things here now is like n to the n squared, right? We can mess with those functions. We can have polynomials inside the powers of n, factorials in the powers of n. I think something that's an interesting exercise for you to do is think about like, okay, where does kn factorial fit in, right? How big is that? Those are interesting things. But there you go. This is my tier list. Again, like what separates like low tier. All right. So for me, let's kind of clean this up a little bit. So for here, just to leave us with some thoughts, I think. So for here, I'll clean all this up. So for B tier and below, all right. So endpoints only. All right. So if I have something like n equals 1 to infinity, like x to the n over anything in the B tier, right? And what's the interval of convergence there? It's going to be -1 to 1, right? Equals 1 to infinity, x to the n squared. It's going to be -1 to 1 inclusive. Okay. So again, it's going to impact, but it's not changing my radius. I'm not dialing and stretching. All right. So for here, this A tier sort of it's by itself here. Why? Because this is gonna scale radius, right? So I have the sum from n equals 1 to infinity of like x to the n over b to the n, right? what's this going to be? It's going to be negative b to b. Okay, so I'm scaling the radius, right? And then this s plus s tier, what's going on, right? Well, here, our radius is positive infinity. Okay, if it's in the denominator, right? So I have the sum from n equals 1 to infinity of x to the n over n factorial. That's negative infinity to infinity. Okay. Similarly, I can make radius equal to 0 by putting it on top. Okay. We can shrink the radius if I put b to the n up top, right? All of these things. Okay. So I think this is like a pretty natural order. All right. Enjoy. Thanks for hanging out.